Now that we've discussed the relationship between mass and moles, and we can figure that out for different formulas, there's a lot of math that we can now do. Okay, so I'm going to start off simple, and these problems do get more complex. These are sample problems. There are many different types of problems that you can encounter. Work your way through them with the same logic as what I'm providing you with here. This is the framework of how to approach these problems. Okay, so let's consider that we have a formula of CO2. Well, we can figure out what the molar mass is of CO2 given a periodic table, and yours may not have as many significant figures when you figure that out. That's fine. So that means that 44.009 grams per mole is the total mass of CO2. So if that's the case, the question is asking you what percentage of that mass is from carbon or from oxygen. So if this is my total, I just need to figure out how much of that mass is from carbon. That's one problem, by the way. And the second question is how much is from oxygen. So to do that, I need to figure out how much mass from CO2 is from carbon to start with. And we do that realizing that there's only a one carbon here, and put the molar or the elemental mass for carbon up top. So there's only one of those. So we have 12.011 grams in every 41.009 grams of CO2. We then multiply by 100% to get a percentage, and we can end up with that value pretty quickly. In the same regard, you can do this with oxygen. Well, oxygen has a mass that's seen here, but there are two of them because there's two of them in the formula. So we have to multiply that by 2 and then divide by the 44. Times 100, and this is what you get. It is absolutely true that you could have taken 100 and subtract out the percentage of mass that was from carbon in this problem in order to get the percentage of oxygen. If that's the way you want to approach that, that's absolutely fine. Another way to look at percentages is that they're fractions of the whole. So in other words, like if you're totaling to 100%, that's the same thing as totaling to one total universe if you divide everything by 100. So that's kind of the way that I look at it. 72% would be, in some mathematical formulas, just 0.72. So watch what you're doing with percentages versus fractions of the whole, okay? That's not something specific, that's just, in general, a note on how those things work. So what we actually just configured was the percent composition of CO2 by both C and oxygen. And what this means is it's just the percent by mass of each element in the compound. You've already done math, you've already figured out something that's really important. Well, you can also analyze percent composition in any sample, not only the molar mass. So you can figure out what percentage of carbon is in a sample if you know how much the sample weighs. So here's a problem as an example here. You have a sample that's 14.23 grams. 8.23 grams of that is carbon, and the rest is hydrogen. So then it's asking you what is the percent composition for both C and H in the sample. Well, again, there's multiple ways to figure this out. Let's start with carbon. Carbon gives a total of 8.23 grams, so that's what I'm going to put at the top, of the total 14.23 grams. And that's what goes in the bottom. You multiply that times 100% and you get your percentage composition really quick. Now, when we're trying to figure out hydrogen, you have to realize that what's left over is hydrogen, right? So if what's left over is hydrogen, we take the total sample amount, subtract out the 8.23 grams that's carbon. If you want to do this before you start the multiplication division, please feel free to do that. And divide that by the total mass of the sample times 100, and you'll get the percentage of hydrogen. Okay. In the next example, we're going to start trying to figure out empirical and molecular formulas from data like this. So let's say that you have a sample that is 0.253 grams in carbon and 1.69 grams of oxygen. Now we're going to do something to the next level. What is the empirical formula of this compound? Well, remember, we know how many grams of each of these we have, and we can convert that to moles. So let's start by figuring out how many moles of each thing we have. So I have this many grams of carbon. I'm going to convert that to moles through the molar mass, and I get this number of moles. So 0.211 moles of carbon is what I have here. On the other hand, if I have 1.69 grams of oxygen, then I take the molar mass here and get that I have 0.106 moles of oxygen. Now guys, it doesn't even matter how many moles you have here. That's just a number. What you need to determine the formula, empirical or not, is you need a ratio between these moles. So to find the ratio between the moles, you take the big number, whichever one it is, it doesn't matter. Don't even worry about that right now. You take the big number, and what I mean by that is 0.211 is bigger than 0.106. And you put that on top, and you divide by the small number down here. Okay, now that means that you're trying to figure out how many moles of carbon you have for every mole of oxygen you have. And that's going to equal about 2 moles of carbon for every 1 mole of oxygen, which means that the empirical formula of this particular compound is C2, because you have 2 of them, for O. So C2O would be the empirical formula. Now, could that be the molecular formula as well? Totally. But we don't have enough information in this problem to be able to tell that. So these types of problems, you need to approach it and go, I need to know what my ratio is between my different elements to form the formula. You can do this in other ways. So I'm down here now. You can start these problems from a percentage. So let's say that you're given, what did I see as an example here? 20.6% is oxygen. You can convert that in your mind to a 100-gram sample, which means that instead of saying 20.6% is oxygen, we can simply say 20.6 grams are oxygen, okay? So it's an assumption, and that's not a bad assumption to make because it allows you to do some math, okay? Here's an example of what I mean here. So the question is, what is the empirical formula for a sample that's 43.642% phosphorus and 53.358% oxygen? Well, we do exactly what I was saying before. We take those percentages and we just assume that our sample is 100 grams. And instead of calling this percent, I'm going to say that's how many grams of phosphorus I have, and this is how many grams of oxygen I have in my sample. So, if I'm starting right here, I have 43.642 grams of phosphorus and need to figure out how many moles that is. So you do that, and bam, that's how many moles you have. You do the same thing for oxygen. And bam, that's how many oxygen moles you have. Just like we did before, we have to figure out what our ratio is. We look for the smallest number. and that is moles of phosphorus. So that's what's going to go on the bottom now. So 3.523 moles of oxygen, see how I did that here, and this number came from here, is divided by 1.409 moles of phosphorus. And what I get is something that can be confusing sometimes, because you ended up with a ratio of 2.5 moles of oxygen for every 1 mole of phosphorus. Well, realize that when you're looking at a formula, empirical or molecular, you have to deal with the whole number of atoms. You can't have half of an atom in a formula. Half an atom doesn't really exist. So we need to take our whole numbers by the end of it. So if I was to write out that formula, it would be PO2.5, which doesn't make sense. So that means that I have to double all of my atoms. So you can sort of see that mathematically as a formula that looks like this. But we're doing this as subscripts because that's how we write formulas, is with subscripts. So this becomes P2O5. Here's how I got that. I multiplied the 2 times phosphorus, and that's where this got doubled, which is a 1 right now. So 1 times 2 is 2. And right now this is 2.5. So I multiply it by 2 and I'll get 5. In another example, let's say that you ended up with a molar ratio of 2.3 or 2.33. You would need to multiply this by 3 in order to obtain a whole number. Okay, so there are times that you need to multiply by more than just 2. And do keep in mind that we can have more than 2 elements in our sample. As a matter of fact, it's pretty rare to have only 2 elements in your sample. If you have different amounts of moles, or say that you have to figure this out for 3 different types of atoms, that's normal. Don't worry about it. Just still divide by the lowest number of moles that you get here, and everything should fall into place, okay? So you can also find, not firm, I don't know where that comes from, find the molecular formula depending on what is given in the problem. And there are different ways to give hints towards the molecular formula. If you're given the molar mass, then that's pretty easy, because you basically take what you have as an empirical formula and you divide the empirical mass by the molar mass. And that's going to tell you what to multiply the entire formula by to get the molecular formula. Here's what I mean by that. Let me apologize for some mistakes on this page that I've already corrected. Okay, so here's an example where you find that the empirical formula is C2H6O. The molar mass of this compound is known to be 138.207 grams per mole. So the question is asking you, what is the molecular formula? So the first thing that you have to do is determine the molar mass of the empirical formula. And so we determined that that's 58.08 grams per mole. So what you do is you say, you know what, that total molar mass that's here must be some factor of what I determined for the empirical formula. So if I divide by what the empirical formula is, that should give me a whole number. And in this case, of course, it does. So what this means is that we now need to multiply each subscript by 3 in our formula. And that's how C2H6O multiplied by 3 ends up being C6, because 3 times 2 is 6, H18, because 3 times 6 is 18, and 3 times the implied 1 that's there for oxygen becomes just 3. And so that is how you determine what the molecular formula would be. Thank you.